In section 13.2, we're going to continue doing calculus with our vector functions. So we're going to be taking a look at derivatives and integrals of vector functions, and I want to start with derivatives. Before we look at derivatives of vector functions, let's just review what the derivative means for a real valued function. If I had y equals f of x. Well, the derivative is just the slope of the tangent line. So if I were to look at f prime of x, that's the slope of my tangent line. And here's how we calculate it. If I had a point there and I wanted to calculate the slope of the tangent line, we'd say that point is x, f of x, and we would choose a nearby point. So I'm going to let the x value of that nearby point be x plus h, so that h just represents a small change in x. We're moving a little ways away from x. And the y value would be f of x plus h. So if here's x, here I've drawn it so that h is positive, so that x plus h is to the right, and then h is actually just that distance between them. If h was negative, x plus h would be to the left, and h would be the signed distance between those points. Once I have 2 points, I can draw in the secant line between them. And I can calculate the slope of that secant line. That would be rise over run, f of x plus h minus f of x, all over the run is h. Now that represents the slope of my secant line. To get to the slope of the tangent line, we simply take the limit as h goes to 0. So as we shrink this little interval so that this point moves closer and closer and closer to this point. So the derivative is the instantaneous rate of change, which is represented geometrically as the slope of the tangent line. And this gives us a formula for calculating it. Now, we've got a perfectly good formula for calculating it for real valued functions, so seems reasonable to see if that perfectly good formula would translate to vector functions. Let's not work too hard to create something new. Let's see if we can recycle something old. So what I'm going to do is I'm going to write out this definition of the derivative, but using a vector function r of t instead. I want to first of all see if the algebraic operations necessary for us to calculate something like this are doable when I'm working with a vector function. And then, if this actually is something that we could calculate, I want to take a look and see, does it actually mean anything? So if I copy that definition, but using a vector function instead, we would get the limit as h goes to 0 of r of t plus h minus r of t over h. So I want to see, are these operations defined for vectors? So r of t is a vector function. This is me just evaluating it at 2 different t values. I can subtract vectors. That's defined. So the top of this fraction is defined. Can I divide by h? Well, that would actually be scalar multiplication. We're taking this vector, r of t plus h minus r of t, and we're scaling it by the reciprocal of h. So yes, that is defined. That's scalar multiplication. Okay, and can I take the limit of a vector? Yeah, we just learned how to do that in the previous section. So this is something we can calculate. Let's take a look and see if it actually means anything and would be useful to calculate. So I'm going to just suppose that I have a vector function. I'm going to draw it in 2 space just because that's easier to draw. And let's suppose my curve is oriented this way. So the arrow again indicates the direction of increasing t. So if I were to have a point r of t on the curve, now of course when I'm drawing the curve, I'm drawing a bunch of points. But it can be very, very helpful in our understanding of vector functions when there are a couple of points in particular that we really care about to draw those as vectors. So there's my point r of t. R of t plus h would be the position vector for another point on the curve. Now I'm going to draw this with h being positive, although just like with real valued functions, h could be negative as well. If h is positive, r of t plus h would be some point a little further along the curve. Okay, so I've drawn in those two vectors. Now, what does the vector difference look like? Well, I know when I subtract vectors, I'm going to get the vector that points from the tip of the one I'm subtracting to the tip of the one I'm subtracting it from. So this right here is r of t plus h minus r of t. Notice that's connecting 2 points on this curve. That would be a direction vector for a secant line. Pretty cool, okay? And what does dividing by h do? Well, all that's going to do is that's going to scale this. Now I said I've drawn this with h being positive, so that r of t plus h is further along the curve. So if I were to scale it by the reciprocal of h, that might stretch or shrink it, but that's going to preserve the direction because h would be positive. So this is not only a direction vector for a secant line, but it's consistent with the orientation of the curve. As we're passing from this point to this point, we are going in that direction, not the opposite direction. Notice if h was negative, r of t plus h would have been over here somewhere. It would have been a point on the curve that we'd hit before we hit r of t. Then r of t plus h minus r of t would have been pointing, it would look like backwards, against the orientation of the curve. But when we scale it by a factor of 1 over h, h would be negative, and that would reverse the orientation. So this right here is a direction vector for a secant line. And it's compatible with the orientation of the curve as we're passing through these points. When I then take the limit of that, what do you think we're going to get? We're going to get a direction vector for the tangent line. So that tells us the significance of the direction of the derivative vector. Now, of course, a vector has both magnitude and direction. The direction is that it's going to be a direction vector for the tangent line. We'll talk a little bit later about what the magnitude means. But I'm convinced, based on this analysis, that yes, it is very reasonable to calculate a derivative of a vector function. And in the next video, we'll actually do an example and find ourselves a tangent line.